Hello, welcome back to Data Analysis for the Humanities, and today we are starting a new section of this about neural networks and machine learning. And when we talk about machine learning, there are many different styles of machine learning, there are many different algorithms, and we will talk about some of them. Some are very straightforward, simple mathematics, but what is the most magical of them, and this is why I want to begin with that, are the neural networks. Neural networks do things that we thought only brains could do, only real biological neurons could do. And in this sense, they're called neural because they are inspired by the neurons of our brain. They don't work in exactly the same way. So obviously, our neurons are biological, and artificial neural networks are made out of pieces of code in a computer. So this already shows that there's a totally different way of working there. But also, artificial neural networks simplify very much the way things work mathematically. They're actually very simple in their design, and the complexity comes only from the scale, right? Because you need to have lots of neurons in order to do something useful. For example, your brain has around 100 billion of them, right? Imagine 100 billion is a big number, right? And we don't yet have artificial neural networks with that size. So let's go have a look now at how these things work, and you will see that we have very interesting demonstrations with Python. We can do lots of interesting things to show how neural networks really work. Okay, so to begin with, there are these words neurons and perceptrons. So neurons is normally used for the biological neurons. You can say an artificial neuron or an artificial neural network, but you have to say it. If you just talk of a neuron, then people will probably think that you are talking about biological neurons. The second thing are perceptrons. Perceptrons is an older word from the 50s, when these were first developed, and is normally used to mean one neuron only is a perceptron. And when you connect many of these perceptrons together, then you get an artificial neural network. This is, as I said, an older term. It's not used much, but it is useful because here we are going to go back to the basics, right? Because we want to understand how they work. It's easier to understand how one perceptron works than to go and try to see how a modern neural network works. For example, the stuff that is in ChatGPT or Facebook to recognize faces. So what do biological neurons look like and how do they work? Here is one. This is a simplified, of course, it's always simplified when we talk about biology, a simplified schematic of biological neuron, what is in your brain or what connects your brain to your muscles or connects your eyes to your brain. So you have always the signal going from left to right here. You see send signal down the axon, it says there, this is the direction of processing. And on the left side of this picture, you have the actual cell. This is the neuron, this is the living cell, and it has inputs. And on the left side are these inputs, and the inputs are called dendrites. Dendro comes from Greek, means tree. So they're tree-like structures, and you can see why they're called like this, because they look like the branches of a tree. And these are the inputs. So neurons don't stand alone, right? They're connected to other neurons. So therefore, these are the inputs from the other neurons. They come in there and then they get processed. We will talk about this in a moment, in this cell body. And then the cell body fires a signal down the axon. And the axon is this long structure. This is like a wire. It's in the simplified, engineering version of it. It is really just a connection. It's just a wire. And this wire then at the end splits into these terminal branches, which are the outputs of the neuron on the right side now. And the outputs of this neuron connect to the inputs of more neurons, right? So this is the idea. And this forms then this network of hundreds, thousands, millions, billions of neurons, right? 100 billion, we said, are in your brain. And they are all connected like this in some way. And now again, the biological neuron is not exactly how the artificial neuron works. There are, of course, differences in the implementation, how the electricity is transmitted, the electrical signals, how the signals are even encoded. But this is the basic idea. And now when we see this in a more technical way, it looks like this here. This is a simplified diagram of an artificial neuron, which is the perceptron we talked about from a researcher called Rosenblatt in 1957, I think. And you can see that again, like in our biological diagram, here the processing goes from left to right. You have the inputs on the left, so this corresponds pretty well to what we saw before. You have the inputs on the left, you have the body of the neuron, which is the thing with a big Greek sigma in there, the round circle, the big round circle, and you have the output on the right. And now what is exactly happening? You have to remember that signals are coming in from the other neurons and they are output again to other neurons from the neuron we are looking at. And to simplify matters now with the calculations, we assume that all these signals are somehow normalized between 0 and 1. And so 0 means I don't have any electrical signal going in, or I don't have any information going in, it's 0. And 1 means I have the maximum strength of information going in. And so you have some signal between 0 and 1 on each one of the inputs, which can come from different neurons. This one neuron we're looking at is connected to. And then each one of these inputs is multiplied by a weight. So I have the weight W1, W2, Wn, depending on how many inputs I have. Every input has its own weight. And what are these weights now doing? They are regulating this input because we multiply the input signal by the weight. And so the weight is again a number between 0 and 1. So if the weight is 0, it does not matter how much the input is, right? Because we're going to multiply it. So the weight is going to kill. If it's 0, it's going to kill the input. We multiply the input with 0, we get 0. Or if the weight is 1, it's going to let all the input through. If the weight is 0.5, it's going to half the input. So the weight is this neuron's way, because this is part of this neuron, it's this neuron's way of controlling how much it wants to listen to the other neurons it is connected to. So it's not like the other neurons can stuff the information into this neuron, totally uncontrolled, but this neuron has control over what it receives. It's like when you hear loud music, you can close your ears, with your fingers, or if a light is too bright, you can close your eyes, and then you can control how much of the signal goes into you for further processing. And this is something the neuron can do itself by adjusting these weights. So the weight is just a multiplication factor between 0 and 1, which I apply to the raw input that comes from other neurons. And now all these weighted inputs, after the weight has been applied, go into this big circle which has the sigma in it. And the sigma, of course, in mathematics stands for sum. So what happens now is that they are all summed up. This neuron is just an addition machine. It adds up all the weighted inputs and produces a sum. And now, if the sum of the weighted inputs is greater than a particular threshold value, threshold means a limit. If it's greater than this limit, then this neuron, our neuron we're looking at, is going to fire a signal on the axon to the right and to its output. If the sum of the weighted inputs is not big enough, it's not bigger than the threshold, then this neuron is going to stay silent and it's not going to fire anything on its output. And now this could be a binary kind of output, like I just described it. It fires or it doesn't fire. It could also be like what you see here in the sigmoid curve, an output that itself goes between 0 and 1, where it can fire a little, or it can fire some more, or it can fire at maximum level. So it can be some kind of regulated firing of this neuron depending on how much the sum of the weighted inputs is bigger than the threshold, for example. So there are many ways of implementing this thing, but essentially this is what one neuron, one artificial neuron, is doing. So we suspect that biological neurons work in a similar way, and actually if you see what artificial neural networks can do, it is very similar to what biological neurons can do. So there is certainly some similarity there in the way they work. There are also certainly differences. And then there's this whole, discussion about, is there anything else to consciousness? Is there a soul? All these things which don't concern us now. But I just want to say, because we are philosophers, right? If you're a dualist, of course, you will question whether this is the whole story. But it doesn't matter, because we are not talking about human souls. We are not talking really about human brains or consciousness here. We are talking only about artificial engineering neural networks. And so they work like that, and they work very well. And it's surprising if you see how simple a neuron is, right? That's all to it. There's nothing more to it. It's a number of inputs. They get multiplied with a factor. They get added up. And if they are greater than the threshold, the sum of the weighted inputs, then it will fire, otherwise it will not fire. And what it fires means it put a signal on the output, and this output then gets distributed to other neurons down the line, which do exactly the same again. And this happens a few 100,000 million times, and this produces intelligent behavior. Right? Because there is certainly intelligent behavior. I'm not saying it produces a soul, it produces consciousness, anything like this, but it certainly produces intelligent behavior. We can have neural networks drive cars, which, a Tesla is doing. We can have neural networks recognize faces, what your phone is doing when you unlock it with your face. So all these things, they produce language, what ChatGPT is doing. All these things are based to some extent on neural networks, artificial neural networks, and they work. So this is a very powerful computational model that we have here. Let us now briefly talk about some words here. The inputs are called inputs, obviously. The factors we are multiplying with are called the synaptic weights. Synaptic weights. So the connection between the input and the neuron is called the synapse. Synapse means, connection point. And because this is a factor that is multiplied with the input, we talk of a synaptic weight. It gives a weight to the input. It makes it stronger or less strong. So the synaptic weights are very important. Synapses are the connection points, and the cell body is considered the synaptic weights plus this unit that sums everything up and checks it against the threshold. And then you have the output, which is called the axon, like in the biological neuron, right? It's the same here with artificial neuron. This fires or does not fire, and then distributes the output to other neurons on the right side. And what is on the right are called the terminal branches. Because they're the end of the neuron, and they branch out to the dendrites of the next neuron. Okay, that's it for the basic idea of what a neuron is and what it is built of. And in the next video, we will talk about how it actually calculates something. So let us stop here, and I hope to see you again in the next one in a moment.